So now let's take what we've learned about the central limit theorem for the sampling mean, and let's compile it all together into one problem. So in the United States, the year each coin was minted is printed on the coin. They have a little year on it. To find the age of a coin, then, you would just subtract the current year from the year printed on the coin. So for example, if I'm making this video in 2015, I pick up a penny and it was circulated, or it was minted in 2000, that's a penny that's 15 years old. Now, the age of pennies are circulating pennies, pennies that are in activity, in circulation, are right skewed. So assume the ages of circulating pennies have a mean of 12.2 and a standard deviation of 9.9. So explain why we cannot determine the probability that a single random penny is over 16 years old based on the information that you get. Well, you know that it's right skewed, right? And the problem is that with a single penny, with a single random penny right there, you're not getting a sample size that's large enough to overcome the skewing, if you will. Okay, so I just typed that up. So here's the distribution of your age of pennies. They're right skewed. And with n equals only 1, because a single penny is 1, because of that, it's not large enough to overcome, if you will, the skewed right shape and ensure normality. We want, at this stage, greater than 30 for the sampling distribution of a sample mean. Now, if n was bigger than 30, then we would be able to find the probability, which is exactly what's going to happen starting down here. So right here, because 1 wasn't enough, I took 40. So now what's the sampling distribution? Well, when we want that, we want the shape, the center, and the spread. Okay, so we know that the shape is normal. We know that because, well, we don't know it, but it's normal enough that we're going to be able to do our calculations. And that's because, I should say it's normal-ish, right? But it's normal, and that's because n is 40 is greater than 30, and you have to say that, right? You can't just say normal. I'll erase the ish, but that's what's actually happening, right? It's because there, because n equals 40 is greater than 30. And you have to explain, and that's what the explanation is. Okay, and also, by the way, we have random and independent. Random independent sample, right? Those conditions that are the conditions for the central limit theorem. So we have that it's normal, we have that, we have that it's greater than 30, we have that it's random and independent. Okay, now what about the center? So the center is the mean of the x bars. Which by definition is the mean, which according to the instructions right up here, look, it says it's 12.2. I'll highlight that in green. So it's 12.2, so that means that it's 12.2. Done with that. Now the spread is, let's see here, spread is the standard error of the x bar, which you can abbreviate it either SE, standard error of the x bar, or sex bar if you want to get all fancy about it, or the sigma of x bar, meaning the standard deviation of the sampling distribution of sample means. And according to the formula, that is sigma over the square root of n, which in our case is 9.9 over the square root of 40. And if you want, you can find a decimal for it, but there's no need, right? I mean, the decimal might be interesting to us, so let me just find it. 9.9 divided by square root 40, 1.565 or so. But even though we don't really need it, it's sometimes handy to have just to know what it was. There we go. All right, now let's use that information to talk about the first quartile of 40 pennies. All right, so let me pull up the decision matrix one second. So if we look at the 8.1 decision matrix, we are wanting to find the first quartile. So quartiles, percentiles, you're looking for an x bar. So we're going to have to use inverse norm. So let me go make a picture and type that up. One second. Okay, so let's remind ourselves that the first quartile is actually the 25th percentile. We learned that back in section 3.4. And that means that you've got the lower part here is worth 25%. You know that the center is 12.2, and what you're looking for is what this x bar is. It's not an x, it's an x bar. You're looking for a sample mean right here. Okay. Since you're looking for a sample mean, it's going to be x bar. So let's type that up. Before we can type it though, we need to go find our decision matrix. So again, we're looking for x bar. We're looking for a quartile. So we need inverse norm, left area, mu, sigma over the square root of n. Okay, so let's type this in. Inverse norm, and then the left area, but the left area is 0.25. The mu was 12.2. We already found that up above. And then the standard deviation was 9.9 over the square root of 40. Right, so we'll just have to find what that is. And that will be our results. So let's go grab a calculator. Okay, clear all this out. Inverse norm is in my distribution menu. So second variables, hit number 3, inverse norm. We got an area of 0.25, a mu of 12.2, and here it's just better to just use the fraction. So sigma is not really sigma, it's sigma sub x bar, which is 9.9 divide, don't forget the division symbol, square root 40. The biggest mistake students do there is they'll forget to do the division. And when you type it and paste it in, it actually just shows up right there, 9.9 over the square root of 40. Enter. So we get 11.144. Now remember what this is. This is 11.144 years because this is the age of pennies. We're finding a sample mean. We're not finding a probability here. So this will be 11.14 years of age. And that's our final answer. All right, now let's do it all again. All right, what is the probability that a random sample of 40 circulating pennies, so it's 40 pennies again, has a mean age greater than 16 years, and would that be unusual? Okay, so 12.2 is my middle. I'm going to need 16, which is over on the right, or larger. So I'm going to go draw a picture of that, and I'll be right back. All right, there we have it. So I have 12.2 right here as my mean. The x bar is, I had to kind of turn them on their side so I could fit all the words in, but x bar is 16. And I'm looking for that area because a probability is the area. Okay, so I want the probability that x bar is greater than 16. There, that's a little bit easier to write it. So area is the probability that x bar is greater than 16. That would be, now let's think, I know my x bar, and I'm looking for, so I know x bar, and I'm looking for area probability, so I'm going to use normal CDF, left, comma, right, comma, mu, comma, sigma over the square root of n. Okay, so this is equal to normal CDF. The left-hand edge of what we shaded is 16. The right-hand edge is 1e99 because it goes on forever. So 16, comma 1e99, comma, and then the mean of 12.2, standard deviation is 9.9 over the square root of 40. All right, so now I've got to go to inverse norm, or excuse me, to normal CDF and find that. So normal CDF, so from 16 to 1 second comma, remember that's where the scientific notation E is, 12.2, 9.9 divided by square root 40. I'll go down to paste and press enter, enter. And I get 0.0076. And there's our result. Now we have to answer the question as well, which is, would this be unusual? So we need to answer that bit. And the answer is yes, this is unusual. Because at this point, unusual for us is anything that is smaller than 5%, and this is smaller than 5%. So a mean age greater than 16 is very unusual, and that's because the probability of this mean age X bar being greater than 16 is 0.0076, and that's less than 5%. Less than 5%, remember, is still our threshold for unusual until about chapter 9, and then it starts being other things, namely alpha. It's going to start being alpha, but until that point, we're going to say 5%. All right, so then suppose that it happens that you get a batch of 40 pennies and you have a mean age greater than 16. What are the 3 possible conclusions you might draw? So we just set up here that it's got a very low chance of having an X bar greater than 16. And then we said, okay, so suppose you do get a batch of 40 pennies and it does have an X bar greater than 16. What are the possible reasons why this might be happening? And the answer is there's 3 of them, 3 broad reasons why this could be happening. Number 1 is usually the one most students think of when they're just sitting in class. They think, oh, the person who you picked the pennies from is a hoarder, or the person's a collector, or they knew what you were going to do that day and they brought their old pennies on purpose, that kind of thing. Okay, so you'd get that sample would be biased, not random. And I just wrote up a couple examples, but I put etc. in there. So the person was tipped off, the person, brought old ones on purpose. Sometimes when I do this in class, students are like, you just handed them a bag of old pennies, things like that. Okay, then the next probability is, or possibility, excuse me, is fluke, which is just random chance, right? Sometimes weird things happen, right? But the problem with that is that we know the probability of this happening by chance. It's right up here. It's 0.0076. That's the probability of it happening by random chance. It's not 0, right? It could happen. It's very low, but it could happen. There. Just by random chance, it happens. Stuff happens. That's what many t-shirts tell me, right? That's what this is. This is the stuff happens, right? Or whatever vulgar word you'd like to put in there. Stuff happens, right? If it's going to happen, it'll happen to me, that kind of thing. So it's just random chance. We just had a patch of pennies that were old. Well, they weren't necessarily all old, but their average was over 16 years old. But the probability of this is very low, right? So that leads us to the number 3. So let me just back up. Number 1 doesn't really get us anywhere as statisticians, because if you do have a non-random bias sample, you basically can't do anything in our course. I mean, statistics is all based on the fact that based on randomness and things being unbiased. So if you've somehow biased the results, then everything is garbage, right? You can't really do much of anything in our course. Now, flukes can happen for sure, but we have to kind of gauge what we think is a threshold for so low that we think something else is going on. 0.0076 is really low. So I'm guessing that a fluke is not really the option, or not really what's happening. Now, it could be wrong. It could just be a fluke. But if I'm not wrong, that means there's got to be something else. So if it's not that it's biased, and it's not that it's a fluke because the chances of it are so low, that leaves you one other option, which is your parameter or parameters are wrong. Now, what are parameters? Well, we learned them back in chapter 1 and chapter 3. They're the things that you assume to be true about your population, which in our case was mu and sigma. So the parameters, like I just said, were 12.2 and 9.9. And what's happening is maybe one or possibly both, so one or both of these are not correct. Maybe they were never correct, possibly they never were right, or possibly they've changed from what they once were. Like the data was gathered, a few years ago, maybe it's not 12.2 anymore, maybe it's something else. And various other things along that. Maybe the mint was wrong. Maybe because that's where I got the information from. So all of those things are possibilities. And that's what you're figuring out. You're figuring out the possibilities, right? And this one in particular is where we're shooting for in chapters 9 and 10 and 11, right? We're going to say that we don't think it's 1 and 2. 1, basically because 1 doesn't lead us anywhere. 2, because we'll say the chances of it are so low that we think something else is going on, and that something else is that you're being lied to, right? You're going to prove, quote unquote, that people are wrong, that something's going on with your samples. So note what this means. If number 2, the probability of that fluke is really, really small, then we're going to start making arguments that number 3 is probably what is happening. That is the basic logic behind all of the rest of this course, and quite frankly, all the rest of your next stats course if you would go on. I mean, this is a really big deal, right? We assume number 1 is not happening, right? And that means leaves us number 2 and number 3. And if number 2 is low enough, then we're going to start saying number 3 is what's actually occurring. There, I just typed up what I wrote a little bit. So you assume number 1 isn't happening, even though it honestly does in real life, but we have to ignore it for stats because it doesn't help us. But that leaves you 2 and 3. But if the probability of 2 is so small, right, that you think something else is going on, that supports the case. I shouldn't say makes the argument, but it supports the case that number 3 is what's going on. Now, we don't know that it's going on. It's probably going on. And that's a big distinction that we're going to make in chapter 10 and 11 and 12. We don't know for sure what's happening, but we think it's more likely that number 3 is what's going on rather than number 2. And this is how we begin to prove, quote unquote, things. We don't really prove them. We just kind of prove that it's likely, right, within a reasonable doubt. Right? You can't really prove things, but we'll prove it's mostly likely that number 3 is what's going on. Somebody's lying, something's changed, something's different. That's number 3. All right, we're all done with that section. I'll see you back here for more lecture videos.